Hello, everyone. Thank you for coming to hear about the design pattern that shall not be named. Now, I'm not going to name the pattern that shall not be named. However, you may know the name of the design pattern that shall not be named, and I remind you, the design pattern shall not be named. Hey guys, thanks for coming. I don't normally explain the hat. I've been doing this for about 10 years now, and I kind of like there to be an air of mystery so you can wonder whether I'm a crazy person. But since there's some room for ambiguity in this talk, I feel like I need to explain that the hat is why I wear the hat for these kinds of talks. One, it's fun and outrageous. Two, I had it laying around because my friends and I went and saw Return of the King dressed up. And why have a Lord of the Rings hat in your closet if you're not going to use it? So here I am. But notably, this is not a Harry Potter sorting hat. And I bring this up because there might be some points of confusion. Also, I suffer imposter syndrome. This is sort of a security blanket that makes me feel like I definitely don't belong. And it's also actually magical. It is capable of performing exactly one trick. I can walk into the middle of a room like this, and then take my hat off, and then I disappear. And that is probably because we all look the same, which is a bigger problem, which probably goes down to the way we hire people and how we welcome people into the software industry. So if I were to take my notes from, say, The Sorcerer's Apprentice, and I hired a broom, and then I came up with a fiendishly clever way to hire more people to work on my project by, hiring for culture fit. Are you broom-like? Or, things like that. And then eventually, inevitably, you have a company full of brooms. So this is my public service announcement. Hire not for culture fit, hire for culture add. Find somebody who challenges you, somebody who increases your perspective so that you can see more collectively. And that is my public service announcement. So, about the design pattern that shall not be named, thank you for coming. There will be no foolish wand waving. We are here to study the exact science and the subtle art of applying the design pattern that shall not be named. You will not find it between the covers of this book. However, you will find patterns in this book that could be extended via the design pattern that shall not be named. Lesser tricks, you might call them. It is a design pattern that is so subtle and ephemeral that even to whisper its name and everyone's confused and no one can understand what it is, it just disappears. It's almost as if there were some celestial force that prevents us from understanding each other once we have obtained the knowledge of the design pattern that shall not be named. It's like you get to the top of the hill and suddenly you're speaking in tongues. Or, alternate theory, it's like you're flying around and the first rule in the instruction manual for flying around is pull up the ladder behind you so nobody else can understand and experience this wonderful thing of flight. So, I propose a different strategy. Instead of telling you what it is or couching it in its jargon or how people understand this typically, I'm going to show you 3 examples from my personal experience where I accidentally, in many cases, ended up using the design pattern that shall not be named. Some of these are state machines. Some of them are promises. Some of them are any number of things. And the thing that they have in common is that they nest like Matryoshka dolls. And some of them are like promises. You can make parsers. I'm going to show you an animation controller I created for a game. They're all state machines and they all nest. There's no sad muse here. What if I told you callbacks could return things? What if I told you that functions that accept callbacks could also return things? Suppose that you had functions that just took callbacks that didn't return things. There might be some missed opportunity. It might open up a whole new world for you. So what is the design pattern? How do we apply it? Well, first you make a function, and then you make the function take a callback. So far, so good. Everybody's with me. And then you make the callback return something, and then you make the function that took the callback in the first place return something of the same type. Yeah? All right. So in other words, yo dog, I heard you like functions. So I made your function take a function so you can return while you return. And that is the pattern that shall not be named. So here's example 1. I'm going to start with bindings. Now, back in the day, there was going to be a day I had to say back in the day, and this is it. Before React, we did these things called two-way bindings, and it was at one point in my life, oh, yes, bindings have many guises and many names. You've probably seen them before. And in this destination web context, we typically call them bindings or two-way bindings or something like that. But in Objective-C, they're called key value observing, which is an extension of key value encoding. In the literature, which you will never read, it's called self-adjusting computation. And if you take it to its natural conclusion, it sort of turns into Prolog. So here's a contrived example of some magical web application framework that never materialized, but parts of it did, where you come up with a language for describing how you want your data and view properties to be bound to each other, and they'll be incrementally updated based off of changes to the data review. And this is the classic to-do MVC. I know you can't see it, but if you squint, there's rows of to-do list items, and each of them has a checkbox for whether they're done. On the top of the page, there's an all are checked checkbox, and there's a none checked checkbox. And these things will always reflect each other because these bindings will propagate the change outward. So if you click on all checked, then all of them will become checked. If you uncheck one, then the all checked button will no longer be true and it'll become unchecked. Likewise, if you then press the none checked, it'll uncheck all of the rest of them. And so this is what I wanted the end result to be, how I wanted programmers to be able to express this, and then, or more to the point, how my customers wanted to express themselves, and it became my job to figure out how the hell to make this actually work. And it turns out that you need the design pattern that shall not be named. So let's build it up from the little bits and pieces that it's made out of. We're going to use a little library that attaches property change observers to an arbitrary object. So the way this works is that it adds a getter and setter to an object for the property that it wants to that you want to observe changes to, and then whenever you access or mutate that property, it'll be intercepted and you'll get a callback. So here I am observing changes to the foo property, and then I change it twice, and you can see on the right that it emits the change events. What if I told you those callbacks returned things? In this case, they return an object that represents the observation, and you can cancel it. This is important because you need to be able to unregister these callbacks and stop listening for changes to a particular object. And because you both have callbacks that return these cancelable observers, you can also return from the parent function an observer that calls into it. And the way this works is that every time you call this function, it returns a new observer, and then before it calls it again, it cancels the previous one. So then preserving some sort of equivalence, some preservation of cancelable observers because they nest. And in this case, I have created this little wrapper method, which not only observes the property, but property changes, but also the initial value. And now I can nest observe property calls to watch an entire dotted path of property names from a root object. And notably, one of the properties that you get out of this is that you could capture the old object that you were observing along the path, and then replace that object later, and it would be, and all of the observers would be implicitly moved, and you would no longer get change observers on the old object. And this blew up into probably the largest README in all of NPM, that describes an entire language of how to do property change observers and how to propagate changes through arrays and how to just make incremental changes to sliding windows in arrays. And then React happened, and this never saw the light of day. Example 2. Last year, my sister and I made a text adventure, and it was called Escape from Peroakru Island. And the way it was just a little puzzle game. And in order to make this work, I needed to have some sort of animation controller so that I could set up where all of the elements on my page are going to be and where they were going, and then execute the animated transitions serially or in parallel, depending on how they were set up. And here's what it looks like. So go in, I get a pumpkin, and I animate a pumpkin into my inventory. And I get a blue flower, and then I have my pumpkin, which I fill with water, and then I take my pumpkin full of water and I ferment my blue flower in it, and then it turns into a giant pumpkin that you can live in, and then you go on to the jungle. Don't ask questions. The way I wanted to express this was through this declarative language where I say, okay, I want to move this item from the inventory to this position in the scene, and that's going to be decomposed into a move part and then a drop part where it disappears later. I want to do the pumpkin and flower move in parallel, and then after that I want to do the drop and then reveal the homestead in parallel. This seems reasonable, right? So in order to do this, I created a function that returns a transition, and I had to create I created a library around building up these composite transitions. And it's a little bit different than promises because these things have to execute synchronously, because every time you yield to the event loop in a browser, that's when the browser takes its cue. Oh, okay, this is what you want to happen. I'll start making that happen. So in one turn, you set it up, and then you yield, and then it goes and flies away. And the primitive that is underneath this is that there's a tail for your current series of animations, and then you can augment that by using then to get the new tail of the series of animations by passing a transition. And the transition function will be called at some point when it's time to execute a transition and return a new tail that gets hooked up into the chain. So let's build it up from atoms. Let's start with a trivial transition function. This is the no-op transition function. When this is called, it will return the tail state of doing nothing, and from that state you can resume at any time, and that's the idle state. So you start your chain with an idle, and whenever an animation completes, it ends with an idle, so that you can resume the next one, and it just executes your transition immediately. If that function happens to return a new state, you use that instead of idle, thereby letting you just conveniently either return or not from these transition functions. Let's build up some more atomic animation pieces. This one is the one on top creates a delay for a certain amount of time. It'll wait that amount of time and then resume the transitions. And the way it works is by constructing a wait, which is similar to a promise, and returning it. And then likewise, draw does the same thing, except it uses a request animation frame to say, I want at this stage of my animated sequence to yield to the event loop so that the browser can pick up my plan. And so wait is built up in much the same way as promise with resolve and the then method. They work in the same way. You call one of these or the other, never both, which is different. And the idea is that you call them one or the other in any particular order. It doesn't matter. You can attach a transition to follow up with first, or you can resume with the next state on another. And the idea is that if you resume before attaching a transition, it will store that, and then when you do attach the transition, it'll execute it. There's free pizza in the back for whoever can figure out the 2 lines I forgot to add to this slide. the so in both cases you're either setting up the next state or attaching a transition to attach to. And then you can start building up combinators like series and parallel. In the case of series, it's similar to that animate function that I showed you first, where you take the tail of your queue of animations and then you concatenate onto it, adding up and building up a new tail, and then you return it. This ensures that all of those transitions occur in serial. Parallel, you build up in a similar way, except that you wait on a group of transitions to complete and then resume the last waiter. So you immediately begin all of the transitions in your parallel, and then wait for them all to complete before resuming. And then that brings you up to being able to take these things and compose interesting animation sequences. Which now that you've seen how that all works, let's take a look at the animated sequence again. Here I am. This was an unrelated transition, just some simple transitions leading up to the grand finale, setting up with a pumpkin and a flower, and then fermenting them. And this is that transition described. So, third, final example, how to build a parser using the design pattern that shall not be named. We're going to build up a little algebra parser that just takes two numbers and adds them or subtracts them based off of what you have in a string that describes a mathematical operation. You can go take these primitives and then build combinators for associativity, left to right, right to left, et cetera, or precedence tables entirely. I'm just going to start with the simple parts. And I'm going to do it in this funky variation of JavaScript that has types, because the types are actually kind of interesting for understanding what's going on. In this case, I'm building this up from a single type, which is the state of your parser. Am I expecting a number? Am I expecting an operator? Is it going to be a number or an operator, and I'm going to do something different? That's captured by what state you're in. And then in any state, we're going to accept a rune from a string, a single character from a string, and then return the new state. And then we're going to drive through these until we get to the end of the file. So this is the function that returns the end of file state. In the end of file state, I'm expecting to get a null terminator, at which point everything's fine. But if I don't get a null terminator, then I am going to reject this as an invalid string and return an error instead. And this is how I'm going to drive. This is a simple function that starts with the state of EOF, which means that I'm going to parse all strings in the empty file grammar. And then I'm going to build up on that EOF to build up a more complicated grammar, but the driver is going to be the same. We will start with a state, and in that state, we will consume every rune in a string until we get to the end. And if there's an error along the way, we'll bail early, but otherwise, we will eventually come to the end of the string and collect the result. We're going to start with some primitives. I'm going to write a parse digit function. The parse digit function is going to expect a single digit and then forward the resulting value to a callback. That callback is going to, via the design pattern that shall not be named, return something interesting. The callback is going to return the state that follows after I have successfully parsed a single digit. And then, and if it's not a digit, I'm going to return an error, which will give the callback an opportunity to make a decision about, well, if it wasn't a digit, I might try to rewind that and do something else. And importantly, you'll see there's a line right after I call the callback where I replay the rune that was not a digit, so that if the callback decides to consume that, it gets called on the next state. And the driver remains the same, except that I've added a single number here. And then when you run this, it'll print the number 1, because that was a valid expression in the grammar of strings that have 1 digit. And then we build up on that. So this is going to be like a clean star. I want to get, or a clean plus, so it was a single character followed by any number of digits, a single digit followed by any number of digits. So I parse 1 digit, and then if that was successful, I know that I've seen at least part of a number. And then I'll go into a new state, which I will go into repeatedly. As you can see, I return back to that state every time I successfully find a digit, building up a larger and larger number with each successive digit that I discover. And then when I find the first non-digit character via the error that I got in my callback, I'm going to send the accumulated number and replay that non-digit character so that it can be consumed by the next state, which in this case will likely be the end of file consumer. And so here we are parsing a value. I've parsed I've parsed 12. I'm going to get 12 on the output line. And then we can build something up from this. This is the grammar of all numbers plus or minus any other number, not accounting for white space. So we parse a value and then we get it. And if I failed to get a value, I'm going to bail early. But if I did get a value, I'm going to then expect to get a plus or a minus. And if I do get a plus or a minus, I will continue into parsing another value. And as you can see, it builds up into this nice little nested state machine where you can build up an arbitrary grammar from these little composable parsing building blocks that all parse a part of the string. And again, I leave as an exercise for fun. How do you build up a precedence table? How do you do plus, minus? How do you add multiplication and division that has higher precedence than this? So your exercises, go home. Build a parser using the design pattern that shall not be named. You can go on, build unary operators, parenthetical expressions, create a precedence level combinator, so you can just take things that take the primitives and then put them in an array of arrays, expressing all of the terms that you want to parse, and each level of a left to right associativity precedence table. And then on the way, you'll discover how to do backtracking by more than one rune, by replaying all of the characters that you consumed in the case that you failed to parse something that you identify. I used this again in that text adventure to build a text adventure language called Ni, which is a parody of Ink. I like to say there are the knights who write Ni. The K is silent, but the N and I are unbearably loud. And this language I wrote up in JavaScript, and this is just a snippet of the state in which you are expecting to get some amount of text, but you might get an interesting operator saying, okay, I want to loop over this. It might be an arrow for a go-to or something like that. It might be an indentation level. And this is all fed by an outline lexer. And you can use this to build non-trivial languages. And one thing that is interesting about this particular one is that you'll note that instead of a function for the state transitions, I'm using an object with a distinguished next method. Handy trick to make things a little bit more debuggable is that you can use an object with a distinguished method and properties that capture things that you would have had in your closure in order to be able to discover what they are while you're debugging, because your closure keeps its secrets. And that's Ni. So, in summary, no sad muse here. Plenty of inspiration to go on by. Bindings, animation controllers, you can make a parser, you could build a promise library, and you can do any kind of pure immutable stateless I/O in some crazy language that you've probably heard of that this is very popular in, but don't look too deep into the abyss. So yeah, no sad muse, or as you might say, use monads. And that's my talk. Thank you for coming. Yeah, I'll take questions.